An electrostatic motor, unlike a typical electric motor, does not rely on permanent magnets or coils of wire to transform electrical energy into mechanical motion. Instead of using changing magnetic fields to produce motion, an electrostatic motor utilizes electric fields between charged surfaces. These electric fields create an attractive or repulsive force between opposite or like electrical charges as formulated in Coulomb's law. Coulomb's law states that electrostatic force is directly proportional to the product of the magnitudes of two charges and is inversely proportional to the square of the distance between the charges. Advantages of an electrostatic motor include the potential for increased energy conversion efficiencies and the lack of a need for rare earth magnets present in conventional motors. For my electrostatic motor demo, I 3D printed a rotor and stator, and as you can see when I take off the rotor, there's empty space inside. There's no coils of wire or permanent magnets involved. It sits on top of a sharpened copper wire, so it spins with little friction, and then the outside is wrapped with copper tape on 8 vanes on the rotor, and then the stator also has 2 electrodes wrapped in copper tape on the left and right sides. So as you can see, when I power it up, the rotor likes to align 2 of its vanes to the 2 electrodes. If I give it a little nudge, it realigns, but if I push it just far enough, it'll eventually accelerate and then reach a constant speed. So I have a DC supply set at 20 volts that's going into a driver board that's commercially available, and then that driver board is connected to a high voltage flyback transformer, which is then directly connected to the 2 side electrodes. I think the reason why the rotor aligns itself to the 2 electrodes when it's initially powered on is that the applied electric field produced by the high voltage transformer causes a charge separation in the copper vanes nearest the electrodes, where opposite charges are attracted outward towards the electrodes and like charges are repelled inward toward the rotor's center axis. The attractive force is the strongest since the minimum air gap between an electrode and the outer edge of a rotor vane is around 1 millimeter, so it's constantly pulling those outer 2 vanes towards the electrodes. When the rotor is pushed far enough out of alignment with the electrodes, the attractive electrostatic force pulls the nearest rotor vanes towards the electrodes with enough acceleration that once the vanes pass by the electrodes, the momentum of the rotor keeps it turning in the same direction. And then the next pair of vanes on the rotor get pulled towards the electrodes in a continuous cycle. The symmetry of the 2 electrodes on the stator and the 8 vanes on the rotor appeared to cause the stabilizing phenomenon. I wanted the rotor to begin spinning on its own without requiring an external force, so I decided to design a new rotor with an odd number of vanes, 9 to be exact. This change was successful, although it did not work perfectly every time. Sometimes the rotor would oscillate at first before accelerating in one direction, but it finally did not need to kick-start it with physical contact. I also observed that raising the input voltage to the driver circuit increases the rotor's rotational speed up to a certain point. At a high enough input voltage, the continuous electric arc bridges the gap between the electrodes and draws several amps of current up to the supply's current limit.